Right now, somewhere in our galaxy, an object the size of a city is spinning hundreds of times per second. It has no fire, no fusion, no ongoing reactions of any kind. It is simply a remnant, a compressed core, a thing left behind after one of the most violent events the universe is capable of. And yet, that remnant contains more mass than our entire sun. Pack the sun into something smaller than the city you live near. Not a metaphor, not an approximation. That is literally what a neutron star is. A sphere, roughly 20 kilometers across, containing 1 to 2 times the mass of the sun, held together by physics that operates right at the edge of what the laws of nature actually permit. And here is the thing that makes neutron stars so extraordinary. As a subject, they shouldn't exist. Not because the physics is wrong. The physics is right. But the conditions required to create a neutron star are so extreme, the margin between neutron star and something even more collapsed is so razor thin that the existence of neutron stars in large numbers throughout the universe is, in a quiet way, almost miraculous. There are an estimated 100 million neutron stars in the Milky Way alone. Most of them are invisible to us, dark, cold, spinning silently in the spaces between stars. Tonight, we are going to understand what they are. Not just the name, not just the numbers, but the actual physical reality of an object that sits at the boundary between matter and something matter cannot become and still survive. Find a comfortable position. Let your body settle. Let your breathing slow. What you are about to learn is not frightening. It is simply the universe being more interesting than anything we could have invented. To understand what a neutron star is, you need to understand what it comes from. And what it comes from is a massive star. Not just any star, not a star like our sun. Our sun is a medium-sized star, a comfortable, stable, middle-of-the-road kind of star that will live for about 10 billion years and end its life as a white dwarf. But some stars are born much larger. Stars with initial masses of roughly 8 to 20 times the mass of our sun are a different category entirely. They burn brighter, they burn hotter, they burn faster. A star 10 times the mass of the sun might live for only 20 million years before exhausting its fuel. Compare that to our sun's 10 billion years. These massive stars don't just fuse hydrogen into helium the way our sun does. They go further. When the hydrogen in their cores runs out, gravity compresses the core until temperatures rise high enough to fuse helium into carbon. When helium runs out, the core compresses further and carbon fuses into neon and oxygen. Then neon fuses, then oxygen fuses, then silicon fuses. Each stage is shorter than the one before. Each stage produces less energy per unit of fuel burned. The star is burning through its options, faster and faster. Silicon fusion lasts only about a day for the most massive stars. And at the end of silicon fusion, what accumulates in the core is iron. Iron is the end point. Iron cannot be fused to release energy. To fuse iron requires putting energy in, not getting energy out. So when an iron core accumulates, In the heart of a massive star, the star has reached the end of its road. There is no next fuel. There is no next stage. The star has been running on the outward pressure of nuclear fusion for millions of years, and now that pressure is gone. Gravity has been waiting the entire time. And now, gravity. What happens next is the most energetic event in the known universe, short of the Big Bang itself. The iron core collapses, not slowly, not gradually, in less than a second. A core, roughly the size of Earth, collapses to a sphere about 20 kilometers across in less than a second. The infalling material reaches a significant fraction of the speed of light. The density of the core reaches and then exceeds the density of an atomic nucleus. And at that point, something remarkable happens. The collapse stops. Not because of fusion, not because of heat, but because the compressed matter reaches a state where it physically cannot be compressed further. The core bounces. The infalling outer layers of the star, which are still rushing inward at enormous speed, slam into this suddenly rigid core and are reflected outward in a shockwave. That shockwave travels outward through the entire mass of the star. It tears the outer layers of the star apart and expels them into space at a significant fraction of the speed of light. The explosion releases more energy in those first few seconds than our sun will release in its entire 10 billion year lifetime. For a brief period, a single dying star can outshine an entire galaxy of hundreds of billions of stars. This is a supernova. From Earth, if a massive star in our galaxy went supernova close enough, we would see a new star appear in the daytime sky. It would be visible for weeks or months, slowly fading as the expanding shell of gas and dust spread outward into the galaxy. The last supernova, visible to the naked eye, in or near our galaxy, occurred in 1987 in the Large Magellanic Cloud, a small neighboring galaxy about 170,000 light years away. Astronomers around the world stopped what they were doing, and at the center of all that light, all that expelled material, all that released energy, something very small and very dense was left behind. Something that used to be the iron core of a massive star. Something we call a neutron star. The iron core that collapsed was made of iron nuclei and electrons. Under the enormous pressure of the collapse, those electrons were forced into the nuclei. Electrons combined with protons to form neutrons, releasing neutrinos in enormous quantities. In the process, the neutrinos flooded outward through the collapsing star, carrying away energy. And what was left was a sphere made almost entirely of neutrons. Hence the name, neutron star. Now, something has to hold this object up against its own gravity. With white dwarfs, we saw that electron degeneracy pressure does this job. But in a neutron star, the densities are so extreme that electron degeneracy pressure has already been overwhelmed. The electrons have merged with the protons. They no longer exist as free particles. What holds the neutron star up is neutron degeneracy pressure, the same quantum mechanical principle that prevented electrons from being compressed further in a white dwarf now applies to neutrons. The Pauli exclusion principle says that no two fermions, no two particles of the same type can occupy the same quantum state simultaneously. Neutrons are fermions. When compressed to the densities of a neutron star, they run out of room. In quantum mechanical terms, they push back, not because of heat, not because of any ongoing process, but because the laws of quantum mechanics forbid them from being squeezed any further. This neutron degeneracy pressure is what holds a neutron star up. It is powerful, extraordinarily powerful. But like electron degeneracy pressure, in a white dwarf it has a limit. There is a maximum mass above which even neutron degeneracy pressure fails. We call it the Thomann-Oppenheimer-Volkoff limit. It sits somewhere between 2 and 3 solar masses. Below that limit, a neutron star is stable. Above it, even neutrons cannot resist gravity. The object collapses further past any known form of matter into a black hole. Every neutron star exists in that narrow window, massive enough to have survived a core collapse supernova, but not so massive that gravity swallowed it whole. That is the razor's edge neutron stars walk. Let's talk about the size. Because the size of a neutron star is where the numbers stop feeling like numbers and start feeling like something your mind quietly refuses to accept. A neutron star is approximately 20 kilometers in diameter. 20 kilometers. That is the distance you might drive to reach the nearest large town. It is the length of a moderate city. Manhattan is about 21 kilometers long. If you stood at one end of a neutron star and walked toward the other, it would be a walk of about 12 miles. You could, in theory, see the other side on a clear day. That is how small a neutron star is. Now, inside that 20-kilometer sphere, there is more mass than in our sun. Our sun is 1.4 million kilometers across. A neutron star is 20 kilometers across. The same mass, the volume that is, smaller by a factor of roughly 1 trillion. Let's try to feel this in different ways. A single teaspoon of neutron star material would weigh approximately 1 billion tons. Not 1 million tons. 1 billion tons. The entire human population of Earth, 8 billion people, weighs somewhere around 500 million tons. A single teaspoon of neutron star would outweigh every human being on the planet combined. Try another comparison. A sugar cube of neutron star matter, roughly a centimeter on each side, would weigh as much as all of humanity multiplied by 100. Mount Everest weighs approximately 800 trillion tons. A neutron star with a mass of 1.4 suns contains roughly 2.8 times 10 to the 30th kilograms of matter. These numbers don't connect to anything in ordinary life. Your brain has no reference point for 1 billion tons in a teaspoon. And That's the point. The neutron star isn't just an extreme object, a stream object. It is a place where the physics that governs your everyday world has been left behind, where atoms, as you know them, no longer exist, where the entire periodic table has been compressed into something that is essentially a single giant atomic nucleus, the size of a city. That is what a neutron star is. Let that settle as your breathing slows. You don't need to hold every number. Just hold the image. A city-sized sphere, heavier than the sun, spinning in the dark right now in our galaxy. We've established what a neutron star is from the outside. Now let's face the interior of a neutron star is one of the most mysterious and least understood places in the entire universe. Not because we lack the mathematics, not because we lack the observations, but because the conditions inside a neutron star are so extreme that our best physical theories begin to disagree with each other about what is actually there. Let's start from the outside and work inward. The outermost layer of a neutron star is called the atmosphere. It is extraordinarily thin, just a few centimeters in some cases. But it matters enormously for what we can observe, because all the light we detect from a neutron star passes through this thin atmospheric layer. Below the atmosphere is the outer crust. Here, atomic nuclei still exist in a recognizable form. They are arranged in a crystalline lattice, a regular geometric structure suspended in a sea of free electrons. The density here is already extreme, millions of times the density of water, but it is the most normal region of the neutron star in the sense that the physics here is relatively well understood. Going deeper, we enter the inner crust. Here, the density has risen high enough that nuclei begin to dissolve. Neutrons start to drip out of nuclei, forming a free neutron fluid that permeates the lattice. This is called the neutron drip point. It is a threshold beyond which matter, as we know it, begins to change into something we have no everyday name for. Below the inner crust is the outer core. Here, nuclei have dissolved entirely. The matter is a dense fluid of neutrons with a small fraction of protons, electrons, and other particles. This fluid is not a liquid in any sense you would recognize. It is a superfluid, a state of matter in which the neutrons flow without any friction whatsoever, no resistance, no viscosity, a perfect fluid. This superfluid has remarkable properties. It can flow in ways that ordinary fluids cannot. It stores angular momentum in quantum vortices. It responds to changes in the neutron star's rotation in ways that are still being studied. And then, at the very center, is the inner core. And here, physics admits that it does not know with certainty what is there. The densities at the center of a neutron star may exceed several times the density of an atomic nucleus. At those densities, neutrons themselves may dissolve. The quarks that make up neutrons the fundamental particles inside them may become free. This hypothetical state is called quark matter. There may be strange quarks present, forming what is called strange matter. There may be other exotic particles, hyperons, Cohen condensats, whose existence at these pressures is theoretically possible, but observationally unconfirmed. The honest answer about what is at the center of a neutron star is that we are not sure. The center of a neutron star is one of the few places in the universe where our best theories of physics, general relativity, quantum mechanics, the standard model of particle physics, all have to work together, and we are not entirely certain how they do. So when you try to picture a neutron star, picture something that is knowable on the outside and genuinely unknown at its heart. A city-sized sphere with a crystalline crust, a superfluid interior, and a center that may contain forms of matter that have never existed anywhere else in the universe since the first moments after the Big Bang. Now let's talk about the spin, because the spin of a neutron star is where the numbers become almost offensive in how extreme they are. Every star rotates. Our sun rotates roughly once every 25 days at its equator. The massive stars that eventually collapse into neutron stars also rotate slowly, majestically, over the course of days or weeks. But when the core of that massive star collapses, something fundamental happens to that rotation. It's the same principle you may have seen in an ice skater. An ice skater spinning slowly, with their arms extended outward, will spin dramatically faster when they pull their arms in. This is conservation of angular momentum. Angular momentum is a property of rotating objects that is conserved in the absence of external torques. When you reduce the size of a rotating object, its rotation rate must increase to compensate. The ice skater's arms are a small change, spinning up from slow to fast over a second or two. A collapsing stellar core is not a small change. It is the collapse of something the size of Earth down to something 20 kilometers across in less than a second. The angular momentum of the original core is conserved through that entire collapse. The result is a neutron star that can spin hundreds of times per second. Let that number sit for a moment. Hundreds of times per second. The fastest spinning neutron stars, called millisecond pulsars, rotate up to 716 times per second. 716 complete rotations every single second. The equator of such a neutron star is moving at roughly a quarter of the speed of light. Not a quarter of the speed of sound. A quarter of the speed of light. The speed of light is approximately 300,000 kilometers per second. A quarter of that is 75,000 kilometers per second. The surface of a millisecond pulsar is moving at 75,000 kilometers every single second. As a point of comparison, Earth's equator moves at about half a kilometer per second due to Earth's rotation. The neutron star's equator moves 150,000 times faster. And all of this spin is a leftover, a relic, an echo of the rotation of a star that no longer exists. The collapse preserved the angular momentum and concentrated into something incomparably smaller. There is something almost meditative about this. While you are lying still, breathing slowly, a neutron star somewhere in the Milky Way is completing over 700 full rotations in the time it takes you to breathe in once, hundreds of times per second. The fastest spinning neutron stars, called millisecond pulsars, rotate up to 716 times per second, 716 complete rotations every single second. The equator of such a neutron star is moving at roughly a quarter of the speed of light, not a quarter of the speed of sound, a quarter of the speed of light. The speed of light is approximately 300,000 kilometers per second. A quarter of that is 75,000 kilometers per second. The surface of a millisecond pulsar is moving at 75,000 kilometers every single second. As a point of comparison, Earth's equator moves at about half a kilometer per second due to Earth's rotation. The neutron star's equator moves 150,000 times faster. And all of this spin is a leftover, a relic, an echo of the rotation of a star that no longer exists. The collapse preserved the angular momentum and concentrated into something incomparably smaller. There is something almost meditative about this. While you are lying still, breathing slowly, a neutron star somewhere in the Milky Way is completing over 700 full rotations in the time it takes you to breathe in once. Not all neutron stars announce themselves. Most are dark, silent, invisible, spinning in regions of space where there is nothing to interact with. But some neutron stars have something extra. They have extremely powerful magnetic fields. And those magnetic fields do something remarkable. When charged particles, electrons, positrons, are accelerated along the magnetic field lines, near the neutron star's poles, they emit intense beams of electromagnetic radiation, radio waves, X-rays, gamma rays. These beams shoot outward from the magnetic poles of the neutron star. Now here is the key detail. The magnetic poles of a neutron star are often not aligned with its rotation axis, just as Earth's magnetic North Pole is not exactly at the geographic North Pole. This means that as the neutron star spins, its radiation beams sweep through space like the beams of a lighthouse. If Earth happens to lie in the path of one of those sweeping beams, we detect a pulse of radiation every time the beam points toward us, once per rotation. This is a pulsar. The first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell at Cambridge University. She was working with a radio telescope when she noticed a strange repeating signal. It pulsed every 1.33 seconds with extraordinary regularity. So regular that for a brief period the signal was labeled LGM1. LGM stood for Little Green Men. The researchers, privately, half seriously, considered the possibility that what they were detecting was an artificial signal, something made. It was that regular, that precise, that unlike anything seen before in nature. Within months, the explanation became clear. It was a neutron star, rotating once every 1.33 seconds, sweeping its beam across the sky. Not a message, not a signal from intelligence, just the universe, being so precisely mechanical that for a moment it looked designed. Pulsars are now known by the thousands. Some spin slowly. Some spin hundreds of times per second. Some are so precise in their rotation that they are used as natural clocks, more accurate over certain timescales than atomic clocks on Earth. A beam of radiation from a dead star sweeping across the galaxy with clockwork regularity. There is a strange beauty in that. A lighthouse with no coast to warn, no ships to guide, just spinning, just pulsing in the dark. Among all types of neutron stars, there is one subclass so extreme that it deserves its own chapter. Magnetars. A magnetar is a neutron star with a magnetic field so powerful that it sits in a category entirely alone. Earth has a magnetic field. It is what makes compasses work. It shields us from solar wind. It is, by any human standard, a significant force. The magnetic field of a typical neutron star is already 1 trillion times stronger than Earth's. The magnetic field of a magnetar is 1,000 times stronger than that. We are talking about magnetic fields 1 quadrillion times stronger than Earth's. At that field strength, the very fabric of the quantum vacuum is affected. Atoms near a magnetar would be stretched into thin cylinders along the field lines. The chemistry that makes molecules, that makes life, would be impossible if you were somehow 1,000 kilometers from a magnetar. The magnetic field alone, not the gravity, not the radiation, just the magnetic field, would be lethal. It would disrupt the iron in your blood. It would tear apart the molecular bonds in your body. But here is the event that best captures the sheer scale of what a magnetar is. On December 27, 2004, a magnetar called SGR 180620 released a burst of energy in about 1/10 of a second. In that 1/10 of a second, it released more energy than our sun emits in 250,000 years. This magnetar was 50,000 light years away on the other side of the Milky Way. And despite that distance, 50,000 light years, the burst was powerful enough to measurably affect Earth's ionosphere. The upper atmosphere of Earth was disturbed by a flash of energy from an object on the far side of our galaxy. Radio communications were disrupted. Instruments around the world detected the pulse. If that magnetar had been 10 light years away, still an enormous distance in human terms, the event would have been catastrophic for Earth. It would have been one of the largest mass extinction events in the history of the planet. And it lasted 1/10 of a second. The universe is sometimes quiet, sometimes slow, sometimes gentle in the way it shows itself. And sometimes it releases 250,000 years of sunlight in the time it takes to blink. We are fortunate that tonight there are no magnetars within dangerous range. The nearest known one is thousands of light years away. You can rest. Here is something worth knowing before you sleep. If you own anything gold, a ring, a necklace, a watch, any gold at all, the atoms in that gold were almost certainly forged in a neutron star collision. Not in a star, not in a supernova, in the violent merger of two neutron stars, spiraling together and colliding. Let me explain how this happens. Some neutron stars are born in binary systems, two massive stars orbiting each other. When one explodes as a supernova and becomes a neutron star, the other may survive and continue orbiting. When the second star also exhausts its fuel and explodes, a second neutron star forms. Now you have two neutron stars orbiting each other. Over millions or billions of years, they radiate energy in the form of gravitational waves, ripples in space-time itself, and their orbit slowly decays. They spiral inward, closer and closer, over unimaginably long timescales, drawing together toward an inevitable collision. When they finally merge, the event is called a kilonova. It is one of the most energetic events in the universe. And in the extreme conditions of that merger, the temperatures, the pressures, the floods of neutrons, heavy elements are forged. Gold, platinum, silver, uranium, all the elements heavier than iron that cannot be made inside a star. They are made here, in the collision of two dead stellar cores, after billions of years of orbital decay. In September 2017, astronomers detected the gravitational waves from exactly this event, two neutron stars merging about 130 million light years away. It was designated GW1 70817. For the first time in history, we watched a kilonova happen. We saw the gravitational waves. We saw the light. We saw the infrared glow of freshly forged gold expanding outward from the collision site. Estimates suggest that event produced an amount of gold equivalent to several times the mass of Earth. Several Earth masses of gold created in a single collision scattered across space to eventually find its way into gas clouds, into forming solar systems, into planets, into oceans, into the ground, and eventually into the hands of human beings who shaped it into jewelry without knowing where it came from. The gold in your possession is a relic of a collision between two dead stars that happened before our solar system even existed. You are already connected to neutron stars. You have been this whole time. Let's return to the question in the title. Why shouldn't a neutron star be able to exist? You now have enough understanding to appreciate the answer fully. A neutron star exists in a window. A narrow, precise, almost improbably thin window between two forms of non-existence. On one side of that window is dispersal. If the collapsing core is not massive enough, or if the supernova explosion is too powerful, the core can be blown apart entirely. No neutron star forms, just expanding gas and dust. On the other side of that window is a black hole. If the collapsing core is too massive, above roughly 2 to 3 solar masses, neutron degeneracy pressure is not strong enough. Gravity wins completely. The object collapses past the neutron star state and continues collapsing into a singularity. A black hole, a neutron star, can only exist if the collapsing core lands precisely within that window. Not too light, not too heavy. And the window is genuinely narrow. The difference between a neutron star and a black hole, in terms of the core mass, is a matter of perhaps 1 or 2 solar masses. In the context of a star that began its life with 10 or 20 solar masses, that is a difference of perhaps 10%. The physics has to work out with a precision of 10% or better for a neutron star to form instead of a black hole. And on top of that, the neutron degeneracy pressure that holds the neutron star up, that quantum mechanical resistance that keeps the neutrons from being squeezed further, is not infinitely strong. It is the last line of defense against gravity. Electron degeneracy pressure held up white dwarfs. Gravity pushed harder, and electrons gave way. Neutron degeneracy pressure holds up neutron stars. And if gravity pushes harder still, neutrons will give way too. The neutron star is not a stable resting place in any comfortable sense. It is a temporary victory of quantum mechanics over gravity, a victory that holds only within a specific mass range, only under specific conditions, only as long as nothing adds too much mass. And yet, there are an estimated 100 million of them in our galaxy. The universe has managed to hit that narrow target 100 million times in the Milky Way alone. Not because it is lucky, not because it is careful, but because stars form and die in such enormous numbers, across such enormous timescales, that even a narrow window gets hit over and over and over again. The improbable becomes inevitable at the scale of a galaxy. That is perhaps the deepest lesson neutron stars have to offer. The universe doesn't aim carefully, it simply tries an incomprehensible number of times, and some of those tries land exactly right. There is a boundary in the universe that we understand in principle, but cannot pinpoint exactly. It is the line between neutron star and black hole. We know it exists. We know approximately where it is. It sits somewhere between 2 and 3 solar masses for the neutron star's mass. Below that boundary, neutron degeneracy pressure wins. The neutron star survives. Above that boundary, gravity wins. The object collapses into a black hole. We call this limit the Tolman-Oppenheimer-Volkoff limit, or TOV limit. The reason we cannot pinpoint it exactly is that its precise value depends on the equation of state of neutron star matter. In other words, it depends on exactly how neutron matter behaves under extreme pressure. And we do not yet know with certainty how neutron matter behaves at the densities found in neutron star cores. This is one of the open questions in modern astrophysics. The gravitational wave detections of neutron star mergers, events like GW170817, are actually helping us constrain this by measuring how neutron stars deform as they spiral together, how their tidal interactions affect the gravitational wave signal. We can learn something about the stiffness of neutron star matter and narrow down where the TOV limit falls. But the precise location of the boundary between neutron star and black hole remains one of the sharpest open questions in physics today. Think about what that means. The most fundamental division in the fate of stellar remnants, the line between the most extreme form of surviving matter, and the complete collapse of matter into a singularity is something we have not fully pinned down. We know there is a line. We know roughly where it is. But exactly where quantum mechanics finally surrenders to gravity is still being worked out. There is something humbling about that. At the very edge of what matter can be, we are still learning. The universe has not finished teaching us yet. Let's pull back now and look at the scale. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Over its roughly 13 billion year history, a significant fraction of those stars have already lived and died. Stars massive enough to end as neutron stars. Those with initial masses between roughly 8 and 20 solar masses make up perhaps 1% of all stars formed. Over the history of the galaxy, astronomers estimate that somewhere between 100 million and 1 billion neutron stars have formed in the Milky Way. 100 million to 1 billion city-sized spheres of compressed neutron matter, each containing more than a solar mass of material scattered throughout our galaxy. And yet, we have only directly observed a few thousand of them. Where are the rest? Most of them are dark. A neutron star that is not a pulsar, that is not beaming radiation toward Earth, is essentially invisible to our telescopes. It emits some thermal radiation from its surface as it cools, but it cools quickly. Relative to white dwarfs, within 1 million years or so, a neutron star's surface has cooled enough that its thermal emission is very faint and extremely difficult to detect at any significant distance. A billion-year-old neutron star is cold, dark, and effectively invisible. They are out there, right now, in the spaces between stars, in the arms of the galaxy, in the regions of space, between us and the galactic center, in the quiet outer disk, hundreds of millions of invisible, city-sized objects, each heavier than the sun, drifting silently through the dark. The Milky Way is not just a disk of shining stars and glowing nebulae. It is full of remnants, full of things that used to shine and no longer do. White dwarfs slowly cooling, neutron stars spinning silently, black holes marking the graves of the most massive stars. The galaxy is partly a graveyard, not a frightening one, a quiet one, a vast, dark museum of objects that once burned with extraordinary violence and now simply drift and cool and wait. Neutron stars are not just extreme objects. They are laboratories, the most extreme laboratory the universe has ever built. Every experiment we can run on Earth, every particle accelerator, every high-pressure chamber, every ultra-cold experiment produces conditions that are mild compared to the interior of a neutron star. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, creates conditions that approach but do not reach the densities found in a neutron star. The neutron star sits beyond the reach of our most powerful machines, and yet it exists in nature, freely available for study, if only we can find clever enough ways to observe it. Gravitational waves gave us one new window. The the merger of two neutron stars in 2017 told us more about the behavior of dense matter than decades of theoretical work alone, X-ray observations of neutron star surfaces tell us about the radii of neutron stars, which constrains the equation of state of their interiors. Pulsar timing, measuring the extraordinarily precise pulse rates of pulsars over years and decades, has revealed orbital dynamics, gravitational effects, and even hints of a background of gravitational waves rippling through the galaxy. Neutron stars are teaching us about the behavior of matter at densities we cannot recreate, about the behavior of gravity in the strongest fields outside of black holes, about the production of heavy elements that make up the physical substance of our world, about the nature of space-time in extreme conditions. They are, in a sense, gifts from the universe, objects so extreme that studying them forces our physics to grow. Every time we observe a neutron star doing something unexpected, our understanding of the universe has to expand to accommodate it. And there is something worth sitting with in that thought. The universe is not finished. Surprise. The densest objects that matter can form, the most extreme environments that exist, are still revealing things we didn't know. We are not at the end of understanding. We are somewhere in the early chapters. We began tonight with a paradox, something that shouldn't exist, but does. You now understand why a neutron star walks that edge. You understand what holds it up, the quantum resistance of compressed neutrons pushed to the absolute limit of what matter can withstand. You understand where it came from. The collapsed core of a massive star that burned through every fuel available to it and then let gravity take over in less than a second. You understand what it contains: a crystalline crust, a superfluid interior, and a center that may hold forms of matter that exist nowhere else in the current universe. You understand what it does: spinning hundreds of times per second, sweeping beams of radiation across the galaxy like lighthouses with no shore. And you understand what it has given us: the gold that exists on this planet, in this room, on your body. If you were wearing any, passed through the collision of two neutron stars at some point in the history of this solar system. You are not separate from any of this. The atoms in your body were forged in stellar cores. The heavy elements in your world were forged in stellar collisions. You are the universe, having assembled itself into something that can lie still at the end of a day and contemplate neutron stars. That is not a small thing. Right now, somewhere in the Milky Way, a neutron star is completing its 700th rotation of this second. Another is cooling. In the dark, invisible, 1 billion years old, drifting between stars with no destination. Another is slowly spiraling toward a companion, beginning the long journey toward a collision that will happen in 100 million years and forge new gold that may one day end up in a world we cannot imagine. All of this is happening right now while you breathe. while your body rests, while the day releases its hold on you, and the night does what nights do. The universe is vast and old, and full of objects that dwarf anything in human experience. And in all of that vastness, on a small planet, circling an ordinary star, in a quiet arm of one galaxy, among hundreds of billions, you are here, resting. That is enough for tonight. Thank you for spending this time with Midnight Lab. Sleep well. The neutron stars will keep spinning without you.